Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 5 of module 11. In the lecture 5 we are going to talk about the variations of the B value and the aftershock sequence. And in the lecture today we are going to cover the concept such as the variations of the B value, aftershock sequence, within which we are going to discuss about the Ohm's law, and then we will be having the summary of today's lecture. As far as the recap of previous lecture is concerned, we learnt about the frequency magnitude relation, that is also famously known as the Richter-Gutenberg recurrence relationship, which relates the number of earthquakes for a magnitude of m, and the relation says that the log of number of earthquake is equal to a1 plus bm, where m is the magnitude greater than or equal to capital M occurring in a given time. The data deviates from the B is equal to 1 line, so which means that most of the times you will find that the B value are nearing to 1, and it may range from 0.6 to 1.4 or 1.5. It may go even higher, but generally it has the value near to 1, and the data deviates from the B is equal to 1 line for very small, that means surface wave magnitude less than 3 magnitudes, because the global earthquake catalog is incomplete with many small earthquakes not detected. So it is saying that the B value, which is generally should be equal to 1, deviates from the B is equal to 1 value, because at the smaller magnitude the global earthquake catalogs are incomplete, because the smaller magnitudes earthquakes such as less than 2 or 1 are very difficult to basically record, and also sometimes the network doesn't have a requirement to record those earthquakes. So earthquake catalogs, since they are incomplete for those earthquakes, so B value may deviate from the 1 line. Modified frequency magnitude relation, since we have said that for the smaller values of the magnitude the B value deviate, similarly for the larger earthquake also the B value deviate, because at the larger earthquake, let's suppose for more than 8 magnitude, then the surface wave magnitude scale will saturate. So in that case we want to replace that surface wave magnitude scale with the more or less robust magnitude scale, that is the moment magnitude scale. So we are going to use the moment magnitude scale in the modified frequency magnitude relation, or you can say modified Gutenberg-Richter recurrence relationship. So that is log of n a1 minus b m. M will be replaced with the moment magnitude, that is log of m naught by 1.5 minus 10.73. So this formula we have already seen in our previous lectures, and when you will rearrange this equation, then it will become alpha minus beta log of m naught, where beta is b upon 1.5, and if b stays around 1, then it will become around 2 by 3. So basically for movements above 10 to the power 27 dyne centimeter, the data are more consistent with beta is greater than 1 than beta is equal to 2 pi 3. Number n of earthquakes with fault area greater than S should obey a frequency area relation like those for magnitude or movement. So log of n is equal to C minus log of S. So S is basically the area or the fault area, and it can be related to maybe the L square if it is a square fault. Then you can basically interchange those values for the dimensions of the earthquake. Now let's talk about the variations of the B value. As we know, approximately B value should be equal to 1, and that should come to equal to 1 over a large period of time for a large areas, and it will be having a significant variations for smaller time and the smaller areas, and the V value of earthquake swarms is often much larger than 1, sometimes approaching to 2.5. So what is an earthquake swarm? It is basically a sequence of seismic events occurring in a local area within a relatively short period of time. So when those earthquake swarms occur, then the B value, when you will calculate, it will come more than 1, maybe around 2.5. So there might be deviations from the B value from the general value that is equal to 1. These swarms, which lack in main shock, are often associated with volcanic regions and may result from processes such as the migration of the fluid or the magmatic fluid or caldera development. The B value also varies regionally, both spatially and with depth. And now look at this example here, that is for the value of B variations along the Calaveras fault in California, and you can see there are some patches where the B value is less than 1, such as this one, there the B value is less than 1, this is the patch, and here also the B value is seems to be less than 1, which indicates that the shorter recurrence time is there for the larger earthquakes. So the reason for these patches are, these patches have been interpreted as possible asperities. Asperities means weak zone or stress concentrations, perhaps reflecting variations in the frictional properties along the fault, which may control the recurrence of next large earthquake and have large moment release during it. Now, if you look at this particular example here, this is for the larger earthquakes deviations. So if you look at the trend that the power law should follow, it should follow this trend here, and it should be like this. But here you can see the larger earthquakes are more, so it is not following the similar trend, and that is happening near to the trench areas or where the large expectation of having a large earthquakes are more. So the number of large earthquakes are more here, that is why this deviation is occurring here. So you can see figure shows earthquake magnitudes and frequencies for the large earthquakes inferred from the geological paleoseismic studies. These observations have been interpreted as showing large earthquakes more frequent than would be expected from the linear relation derived from the instrumental data. Now, if we look at this example here, this is for the continental interior, where you can consider the smaller earthquakes are more frequent than the larger ones, and it is basically shown by this regular B value slope line. So it should follow this trend, but there is a deviation, and it indicates that the larger earthquakes are not that frequent in the continental interior. So this is what it is written here. A study using seismological data for continental interiors finds that the largest earthquakes are less frequent than expected from the smaller earthquakes. Here in this particular figure, the same power law is basically shown, and the slide says that these observations are interpreted as showing a possible small deviations towards higher frequency at about magnitude 7, followed by a significant decrease as observed in global data, presumably due to finite fault width. The Gutenberg-Richter relation can be modified to describe the different deviations from the linearity. Now, you can see the deviations in the large earthquakes and the smaller earthquakes. So there is always a considerable amount of scatter for the frequency magnitude relation. So this is what it is written here. Some deviations of the largest earthquakes in an area from a linear frequency magnitude relation may reflect a small sampling. So these deviations that you are seeing here you have this deviation for the continental interior, here at around the trench area, this deviation is there where the larger earthquakes are happening more. So this may be due to the smaller sampling of the data. Maybe the number of earthquakes that we are sampling are very small, due to which the deviations are happening. The frequency magnitude relations for the subset have considerable scatter, and the scatter you can see smaller number of earthquakes are following a regular trend, but there is a scatter at the larger value of the earthquakes. So this larger value of the earthquake has having a considerable amount of scatter. So this is what it is written: the largest earthquake appear in some cases more and in other cases less frequent. So if you can see, like here the largest earthquakes are more frequent and here the largest earthquake are less frequent. So this is the deviations that it is providing to the B value estimation. Thus, the B value is reasonably well estimated from the smaller earthquakes but not the largest ones. Now let's talk about the aftershock sequence, that is the Omri's law. And if you remember when we talked about the seismic cycle, where we talked about the 4 stages, and after the co-seismic stage we had the post-seismic stage where the aftershock sequences occurs. So how the pattern of the aftershock sequence looks like, that is described by Omri's law. So aftershocks occur on or near the main shock fault plane. So their locations are used to distinguish between the fault and auxiliary planes and to estimate the fault area. The largest aftershocks is usually more than a magnitude unit smaller than the main shock, and the aftershocks have a size distribution with B near to 1. So the total energy released by aftershocks is usually less than 10% of that of the main shock. The decay of the number of aftershocks is represented by Omri's law, and Omri's law says that the decay in the number of earthquake, or the you can say the frequency of the aftershocks at a time t, that is indicated by n, is equal to C, capital C, divided by k plus t to the power capital P, where n is the frequency of the aftershock at a time t after the main shock, with k, c and P are the fault dependent constant, and P is typically about 1. So here the aftershock sequence looks something like this. You can see like there was a main shock after which the aftershocks are occurring, and when you have your aftershocks in and about the same time of the main shock, then the number is more, and as you go in time, then it decays in a quasi hyperbolic manner. So this is what is written here: the magnitude 5 are 2, 4 are 20, 3 are 65, 2 are 384, 1 is 1855, and greater than 1 is 2434. So total number of aftershocks are around 4760. So this is for the Loma Prieta earthquake, and that is recorded by noon on the November 7, 1989. The diminishing number of aftershocks with time is typical for large California earthquakes. So most of the aftershocks occur soon after the main shock, and the remainder decay with time in quasi hyperbolic manner. The decay of aftershocks reflect stress readjustment following the stress changes due to the main shock. There is an intriguing exception to the Omri's law. So basically, if you go deeper, so most deep earthquakes have many fewer and often no detected aftershocks, and this difference may reflect deep earthquakes resulting from phase changes in mantle minerals, which could produce slip only once on a fault surface, in contrast to the frictional sliding which can recur. So this is the summary of the entire module. Now let's have a look. The general form of earthquake magnitude is, this is the empirical form of the magnitude scale, that is m is equal to log at base 10 a by t. A is the amplitude of the signal, t is the dominant period, plus f as a function of hypocentral depth comma distance plus a constant, or you can say regional scale factor. So the Richter magnitude scale can be represented by this formula, and the originally Richter developed a scale that was for Southern Californian earthquakes, and it was valid only for that region, but later on some upgradation was done onto the Richter magnitude scale and a local magnitude scale was devised. It was something like this, where A is the amplitude and delta is the distance. Body wave magnitude is represented by m in subscript b, and that is equal to log 8 base 10 a by t q h comma delta. Surface wave magnitude ms is equal to log at base 10 a by t plus 1.66 log at base 10 delta plus 3.3. Body and surface wave magnitude do not correctly reflect the size of large earthquakes and saturates at about 6.2 and 8.3 respectively. There are uncertainties in magnitude estimation due to the Earth's variability and deviations from the mathematical simplifications used. Different techniques such as body waves, surface waves, geodesy, geology can yield different estimates. Moment magnitude is given as mw is equal to log m0 by 1.5 minus 10.73. It gives a magnitude directly tied to earthquake source processes that does not saturate. Seismic movement is the scale factor for the spectral amplitude at low frequencies, that means omega tending to 0. This is the reason why it is called the static movement and defined as m0 is equal to mu ds. D is the slip, s is the area, and if you will just expand it further, then it will be mu d fl square. F is the shape factor and L is the dimension of the fault. The rupture time needed for rupture to propagate along the fault is approximately Tr is equal to L upon Vr. Vr is sometimes between 0.6 to 0.9 beta. The rise time needed for the dislocation to reach its full value at any point on the fault has been predicted to be about Td is equal to mu d bar by beta delta sigma. Delta sigma is the stress drop and mu is the shear modulus, and that can be further equated to 16f to the power 1 by 2 divided by 7 beta pi to the power 1 by 1.5, where delta sigma is the stress drop in the earthquake. Once the movement exceeds 5 into 10 to the power 27 dyne centimeter, 20 second is to the right of the second corner. So this is what it is explaining why the magnitude saturation occurs for body wave magnitude scale. So body wave magnitude scale is generally calculated for the seismic wave pulse for the surface wave having the period around 20 seconds, that is mostly for the relay waves. So when you look at this, then as you increase the movement, then the second corner will get away from the flat spectrum on the omega to the power minus 2 portion of the spectrum. Thus ms saturate at about 8.2 even if the movement increases. Ms saturates even as the movement and the fault area increases. Mb saturates at lower moment, that means about 10 to the power 25 dyne centimeter, and remains about 6 even for much larger earthquakes. The relationship between the slip in an earthquake, its fault dimension and its seismic movement is closely tied to the magnitude of the stress released by the earthquake or stress drop. The best constraint quantity is the seismic movement, so we estimate the average slip, that is d vector, from the seismic movement as d vector is equal to cm0 by mu l square, where c is the factor depending upon the fault shape. Stress drop is given by delta sigma, that is cm0 by l cube is equal to cm0 by s to the power 3 by 2. So that I have already explained in the previous lecture. The stress drop on a circular fault with a radius r is delta sigma is equal to 7 by 16 m0 by r cube. Stress drop on strike slip on a rectangular fault with length L and width W yields delta sigma, that is stress drop 2 by pi m0 by omega square L. Stress drop on dip slip on a rectangular fault can be written as delta sigma is equal to 4 lambda plus mu m0 by pi lambda plus 2 mu omega square L. It can be also further written for the Poisson solid, where lambda is equal to mu. Small differences in time function duration correspond to larger differences in stress drop even for an assumed rupture velocity and fault geometry. Stress drop both characterizes earthquake source spectra and gives insight into the physical into the physics of the faulting. The ratio of the slip to fault length is constant, indicates that the strain release in earthquakes is roughly constant at about epsilon xx is equal to d by L, that is equal to delta sigma by mu, that is further equal to 10 to the power minus 4. Although B value approximately equal to 1 over long time scales and large spatial scales, significant variation occur on smaller scale. The B value of the earthquake swarm is often much larger than 1, sometimes approaching 2.5. Thus, the B value is reasonably well estimated for smaller earthquakes but not the largest ones. The decay of number of aftershocks is represented by Ohm's law, and Ohm's law basically defines the pattern of the decay of the aftershock after the main shock. So, and that is the frequency of the aftershock at a time t after the main shock is given by C upon K plus T to the power P, and it is a quasi hyperbolic pattern of the decay of the aftershocks, where n is the frequency of the aftershocks at a time t after the main shock, with K, C and P are the fault dependent constant, where P is about 1. So these are the references of the module, and with this we are going to finish the module 11. Now we are going to start with module 12. Thank you so much. Bye bye.